Welcome to the lecture. You may recall that in the earlier lecture we had discussed about different types of diagnostic tests and diagnostic statistics which help us in checking different types of assumptions and various aspects of multiple linear regression modeling on the basis of given sample of data. Continuing on the same line, in this lecture we are going to discuss some more diagnostic which helps us in checking the violation of basic assumptions of multiple linear regression model and some other aspect. So, let us start with the first aspect, and we are going to discuss here a lack of fit test for regression model. Right. What do you mean by lack of test? In this case, we are assuming that all assumptions of linear regression model are satisfied, and only the linear relationship is in doubt, is doubtful. Right. So, we are going to test about a situation where we want to discuss whether the model has got a linear relationship or not. So, if I try to draw such a situation, this may look something like this, that we have a situation in which we are going to have a scatter diagram something like this. Right. So, in this case, if you try to fit a regression line, that may go like this. Right. So, in this case, we are not really confident whether a linear regression model can be fitted or not. So, our basic objective here is to determine if there is a systematic curvature present or not. So, in order to develop a test for such a diagnostic, we require replicated observations on Y for at least one level of X. So, we are going to illustrate this test using a simple linear regression model, and we consider here a model Y is equal to beta 0 plus beta 1 x plus epsilon, and we have availability of n sets of observations which are going to satisfy this model. Okay. Now, suppose we have ni observations on xi, right. So, now let this yij denote the jth observation on xi. So, here I goes from here 1 to here, say here m, and j goes from here 1 to here, say here ni. Okay. And n is equal to here summation I goes from 1 to here m ni. This is connoting the total observations. Okay. So, now let us try to develop this test. So, now let us try to understand the test. This test is developed by partitioning the residual sum of squares into two components, and this is denoted as say SS res. This is the residual sum of squares, and this is going to be partitioned into sum of squares due to pure error, and this is denoted by SSPE, and another component which is the sum of squares due to lack of fit. So this is actually sum of square due to pure error, and this is sum of squares due to lack of fit. Okay. And you know that the sum of squares due to residual, it has something like I goes from 1 to here m, j goes from 1 to here ni, yij minus y hat I whole square. Yes, you have to keep in mind that here now we have observation on y at two levels, that is I and j. So the earlier definition of sum of square due to residual, that summation I goes from 1 to n yi minus yi hat whole square, that has to be extended with the double summation. Okay, and this can be broken into something like I goes from 1 to m, j goes from 1 to here ni, yij minus y bar I whole square plus sum of square due to lack of fit, and this is given by here I goes from here 1 to m ni y bar I minus y hat I whole square. So if you try to see here, the sum of square due to pure error is given by this, and sum of square due to lack of it is given by this. Okay. Well, I am skipping the minor detail, but by looking at this expression, you can now see that it is not difficult to obtain. This is just obtained by adding and subtracting y bar I in the expression yij minus y hat I here. Okay. Now, when we talk about the distribution, then this sum of square due to residual, see, this has got degrees of freedom as say here n minus 2, and sum of square due to pure error, this has got degrees of freedom n minus m, and sum of square due to lack of it, this has got degrees of freedom m minus 2. Okay. And why the quickness is here too? Because we are estimating two parameters, beta 0 and beta 1 here. Now, based on that, we can define the test statistics. Well, again, I would say that I am not considering here the minor details. Well, there is a strong theoretical proof available for this test. The test statistics is denoted by, say here, f naught, and this is given by sum of squares due to lack of fit divided by its degrees of freedom upon sum of squares due to pure error divided by its degrees of freedom. Right, and if you try to see the sum of squares divided by the degrees of freedom, that is nothing but the mean square due to LOF, the lack of fit, and mean square due to pure error. And this follows our F distribution with the degrees of freedom m minus 2 and m minus m if true relationship is linear. Right. So, in order to compute the lack of fit, what we have to do? We simply have to compute the statistics f naught, and then we have to make a decision here that regard the regression function to be nonlinear if f0 is greater than the tabulated value of f at alpha level of significance with m minus 2 and n minus m degrees of freedom, where alpha is the level of significance. Right. Okay. So, now using this test we can conduct or we can verify whether the regression function is following a linear trend or not. And yeah, this test essentially is a part of the software outcome. So whenever we are going to deal with the software, I will try to show you later on that the sum of square due to pure error and sum of square due to lack of fit, they are the two components of the sum of square due to residual, and they are very clearly mentioned. Okay. So now we come to another aspect, and we would like to check the assumptions using some graphical techniques. Okay, up to now we have discussed the different types of diagnostic which are based on certain statistical format. Okay, so first of all I would try to test what about the linear relationship. Once we have a sample of data, the first step is to verify whether the data is following a linear relationship or not. So, and this gives us the first hand information. So, in the case of a simple linear regression model, it is not difficult, as we have earlier discussed, that we simply need to plot here a scatter diagram between x and y, and if we are getting a trend like this one, yeah, one can see here that possibly a linear model can be fitted over here. And on the other hand, in case if we are getting a relationship like this one, in which we have got a curvilinear relationship, this shows that, well, here possibly non-linear relationship is more suitable, right? Okay, and this indicates the linear relationship. Here you have to be a little bit careful. For example, in this particular case of non-linear relationship, one can always transform the model so that it becomes a linear relationship also, but that will be our secondary step. And in say another case, for example, when we are trying to deal with a multiple linear regression model, then we try to use the multiple scatter diagram. Okay. So I try to draw here a multiple scatter diagram with when we have suppose two independent variables, right? So in the case of multiple scatter diagram, it tries to give us the sort of scatter diagram among all sorts of variable. For example, here if I take say here y, here x1, here x2, and here y, x1, and here x2, so that here I am trying to consider here a model like y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus here epsilon. Okay. Now, in this case, we will try to see on the diagonal elements, we are going to get a relationship between y and y, x1 and x1, and x2 and x2, which has no meaning for us. Now, here if you try to see here in this block, we will be getting a relationship between y and say here x1, and here I will be getting a relationship between y and x2. In this block, I will be getting here a relationship between x1 and x2. Now we try to look at the scatter diagram. For example, it is giving us a like this diagram, and it is giving us a diagram like this one. So this is possibly showing that the linear relationship between y and individual independent variable, say here in this case x1 and x2, has got a linear trend. And so we can expect that the joint relationship between y and x1, x2 may also be linear. One point where I would like to make all of you cautious is that these are only the indicative, right? Because we are essentially interested in finding out the joint relationship of x1, x2 with respect to y. or say when we have k independent variable, then the joint relationship of x1, x2, xk with respect to y, right, up to 3 dimension, possibly I can make a plot, but when I am going to more than 2 independent variables, like a 3 independent, 4 independent variables, and we try to plot them with respect to y, then making a 4-dimensional plot or 5-dimensional plot or say higher order plot, it is not possible. So we have to depend on this say 2-dimensional plots, and by drawing the information on this 2-dimensional plot, we try to conclude about the joint relationship of all independent variable with respect to y. So these are only provide us a sort of indication whether the linear relationship can be fitted to the given set of data or not. Now in this block you will see we are going to get a relationship between x1 and x2, and what we expect that they are not going to show us any trend, because we have assumed that all x1, x2, xk, they are independent by assuming that rank of x matrix is equal to k. Okay. So later on I will try to discuss that that how to verify this thing, that whether all x1, x2, xk are independent or not. But here also I can just inform you that by looking at this type of graphics or some part of this multiple scatter diagram, we can also conclude whether our x1, x2, xk are independent or not. So this is essentially a multiple scatter diagram, and sometimes this is also called as matrix plot, right. Now what about these three one, this one, and this one? So we can see that this is a symmetric diagram. Symmetric diagram means that whatever is the relationship between y and x1, that is going to be the same relationship between x1 and y. So this and this will have a same picture, and similarly this and this will also have a same picture, and similarly this and this, they are also going to have a same picture with some with suitable modification in the trend. Okay. So this is about the checking of assumption of linear relationship between say x and y. Now we come to another assumption. One of the assumption we had made that the covariance matrix of epsilon is sigma square I, right. And suppose now we assume that this is being violated, and we assume that variance of epsilon is given in the form of a diagonal matrix of sigma 1 square, sigma 2 square, sigma n square. So this is like this: sigma 1 square, sigma 2 square, sigma n square, and all of diagonal elements are 0, indicating that epsilon 1, epsilon 2, epsilon n, they are independent, but they have got different variance. In this case you can see that the variance of yi is same as the variance of epsilon I is equal to sigma I square. So now the first question comes that how such situation can be identified in real life. So one factor can be your own involvement with the experiment. For example, if I take a simple example, that suppose somebody starts learning the typing. Now on the first day he is given a sheet of paper and he is asked to type it on a typewriter. On the first day he has no idea, so possibly he will make suppose 100 mistakes per page, and he is going to take this 1 hour at a time. Now he practices say for about a week, and after a week he repeats the same test, that he is given a sheet of paper and he has to type it. So obviously after a week's practice, the number of mistakes are going to be lower than on the first day. And similarly, if he continues to practice more, the number of mistakes are going to be lesser. So in this case, if I try to see get the variability of the number of mistakes that is decreasing as the time is increasing, or the time of number of practicing hours are increasing. Similarly, if I take another example, that as the salary increases, the variety in the consumption of food that also increases. For example, if somebody has a lower salary, possibly he would try to have a simple food at his home, but as the salary increases, the variety in the food increases, and possibly when the salary becomes more, they may also like to dine out in a good restaurant and so on. So, in this case we can see that the variability in the food consumption that is increasing with respect to salary. So, in both the cases the variance does not remain constant. In the first case of typing, the variance is decreasing, and in the second case the variance is increasing in case of salary versus the food consumption. And this problem is actually called as problem of heteroscedasticity. Okay. So, now in case if I want to know whether my data has got a heteroscedasticity problem or not, so we have two options. There are some statistical tests are also available, but all such tests they are based on one strong assumption that the problem of heteroscedasticity is being caused by a particular reason. So, anyway, we are not going to discuss those analytical tests, but we are interested here in diagnosing such a problem using some graphical procedure. Okay. So, in this case what we try to do, that we find the fitted value yi hat and we find the residuals. In this case we can find either the residuals or their scaled version. And in the second step we plot a graph between yi hat and residuals or their scaled versions. Now, depending on the situations we can have different types of pattern, and based on that we try to take a proper decision. So, now I have plotted here some types of pattern. Right. So, one, you can first have a look over this slide. On the x axis I am plotting yi hat, and on the y axis I am plotting the residuals, and I have made here 5 different types of pattern, and based on that I will try to show you that how do we conclude about such a thing. So, now let us try to come to the picture number here 1. Okay. Now, in this case you can see here that the blue dots that are indicating the observations between yi hat and residual, right, they can be contained in a sort of horizontal band. Right. So, here in this case residuals can be contained in a horizontal band. Right. Or I would say that the observations are fluctuating randomly inside this band, and this implies that there are no obvious defects. And variance of epsilon I is constant. Right. Similarly, in the second case, if you see, we have here a trend in which I can contain all the points in a sort of outward opening funnel. Right. So, in this case all the points can be contained in an outward opening funnel. Okay. And in this case we can conclude that variance of epsilon I is not constant. And we further conclude that variance of epsilon I is increasing with observations on yi. Okay, so this is our figure number 2. Now, similarly in the figure number here 3, this is just opposite to the figure number 2, and in which all the points can be contained in an inward opening funnel. Right. So, in this case all the points can be contained in inward opening funnel, and in this case also we can conclude that variance of y epsilon I is not constant, and it is just opposite to figure number 2, that variance of epsilon I is decreasing with yi. Okay. Now, similarly in figure number 4 we can see here that all the points, they can be contained in a sort of double bow, and this also indicates that variance of epsilon I is not constant. And it is indicating that the variance of y is first increasing and then after that it is decreasing. So, this possibly indicates that maybe the yi is a variable in which the values are lying between 0 and 1, and one possibility is that this can be a binomial or Bernoulli distributed random variable. Similarly, in the fifth graphic we can see that all the points can be contained in a sort of non-linear band. Right. So, in this case we can conclude that there is a non-linear relationship between y and say here xi's. Right. And obviously that we cannot conclude here about the variance of yi. So, these are some graphical procedure which can help us in testing different types of situation where one can conclude if the variance of epsilon I remains constant or not. Okay. And these graphics can be prepared using any statistical software. One thing I would like to advise, that in real life whenever we are trying to interpret such figures, it requires some experience also, because these figures may not exactly be like inward opening funnel or say outward opening funnel or a bow. By adding or deletion of some of the points the curvature may change. So, we need to have some practice and some experience before we can draw correct statistical inferences from these pictures. Right. Okay. After this, let us try to consider another situation in which we are going to talk about that we want to verify that epsilon 1, epsilon 2, epsilon are independent or not. Right. So, now these types of thing they are quite possible in practice, and in such a cases the entire time series analysis comes into picture, and all sorts of concepts like autocorrelation, autocovariance, they come into picture. So, it is not really possible for me to discuss all the details over here, but certainly I will try to give you some basic guidelines. Okay. The first thing is that there is a test what is called as Durbin-Watson test, and this Durbin-Watson test this tests the presence of first order autocorrelation in the data. And similarly, we have some other tests also. We are more interested in knowing about some graphical tools here. In order to construct this graphical tool, we try to plot the residuals with respect to time, and we have a set of similar pictures that we have considered in the earlier case, and based on that we try to take some correct statistical inferences. So, if you try to see, I have made here 5 figures, and based on that you can see here that in the figure number 1, all the points can be contained in a horizontal band. And here on the x axis I have considered the time, and on the y axis I am considering the residuals, or even their scaled versions can also be considered. In the figure number 2, we can see here that, like as in the earlier picture, all the points can be contained here in a sort of outward opening funnel, and in this case all the points can be contained in an inward opening funnel. In this case all the points can be contained in a double bow shaped, and in this case all the points can be contained in a non-linear band. Right. So, similar to the conclusion that we had drawn in the case 2, we can also draw here the same conclusion. For example, here I would say that there is no problem, and with this type of picture, when all the points can be contained in a horizontal band, this indicates that all the epsilon 1, epsilon 2, epsilon n, they are independent of each other. In this case, I would say that there is a problem, and epsilon 1, epsilon 2, epsilons i's are not independent. And in this case, rather we can conclude that variance of epsilon I is increasing with respect to time. And the similar conclusion can be drawn in this case also, when all the points are contained in an inward opening funnel, that epsilons i's are not independent, but variance of epsilon I is decreasing with respect to time. Right. And similarly here also the epsilon i's are not independent, but rather we expect that yi's are lying between 0 and 1, and this can possibly be denoting a Bernoulli or binomially distributed random variables. And in this case we conclude that there exists a non-linear relationship between y and xi's. And these graphics again can be obtained using any statistical software. So, now we stop here, and in the next lecture I will try to discuss about the diagnostic tests using graphical procedure for some other assumptions like normality. Till then, goodbye.